And last but not least, I don't think, Stefan, you need an introduction other than Professor of Applied Mechanics and Postgraduate Program Leader for Lift Engineering at University of Northampton and co-chair of the conference. Over to you.
I think, okay, that's working. Thank you very much for the introduction, and thank you for being here. This is the last presentation, so you must be very tired. I will do it as painless as possible. Okay, so the outline of my talk is as follows. I will short introduction. We'll focus here on specific aspects of the problem, which means guide rail design and what kind of loading is to be applied. And that will be deflections and bending. There are some other loads which are possible, where I mentioned in the paper. And later I would show some aspects of ride quality, how ride quality is affected by deflections mainly, but also that could be linked with the stress. And obviously there will be some conclusions. So the basis of this paper comes a few years ago when we looked at EN 81 2050 and the new requirements about deflections of guide rails. And that's some reflections here. Okay, so let's go on. The guiding system is the most important interface between the lift installation and the building structure. The quality of lift installation is founded on the quality of the guiding system. The safety codes impose limits on the permissible stress and deflections to be evaluated at the worst case conditions. And to do that, we have got in the codes quite straightforward models. So I will explain some fine aspects of those models. They are very simple, but there are some aspects which I found not everyone knew. Okay, so what I'll be doing here, there will be straightforward models that we would not be, I will not be discussing a CAD, okay? However, the CAD can be used, and we know that FEM analysis is one of the approved, code-approved methods that you can do analysis. I will show the straightforward models, which are simple analytical expressions coming from classical mechanics. Okay, so that's, we would have issues like, I will demonstrate this in terms of what would need to be spacing of brackets to meet the requirements, for example, of deflections. And we know that there is a straightforward way to do it. So I will show also some numbers here to illustrate those before make some further work in terms of more complex scenarios. Okay, so we know that in EN 81, it is and other codes as well, the guides are considered to be subject to different range of loads. And here in examples, everyone knows it's subject to bending. Okay, the older code is also saying that there's a twisting. Yes, it does. However, when you do bending of the flange, this actually can accommodate this. And also we have a buckling and different scenarios, and everything is based on the worst case scenario. So that's straightforward models in EN 81 2050 are based on the worst case scenarios. So what the models are and whether they are sufficient to make the judgment and how confident we are with the results. That's basically everyone knows that that is affected the design. Okay, so deflections should be evaluated on the worst case condition. Okay, so that's we know. So for example, safety, gear operations, acceleration, decelerations. Obviously that is linked to this equation here, which accommodates the dynamic conditions. Because we look here, EN 81 5020, clause 5, 10, 6, has got these two formulas when you are bending in two directions, y and x, okay? And we know very well, everyone seen those. And, okay, the point is here, the first questions which was is established here, the coefficient 0.7. Where does it coming from? Because everyone probably see and know from fundamental mechanics, but then we take just this here, so this blue formula, that's for simple, simply supported beam. So we are not using simply supported beam model to evaluate deflections in guide rails. It's something else. So what it is? Does someone know? I'll give an answer right now. So basically, this coefficient alpha here, if we use this, would be 1, but it's not. It's 0.7. Okay, the answer is actually quite straightforward. If we look here, if we take classical, simple model when the guide rail is treated as a multi-span beam, subject to lateral loading, okay? So we've got a load which is, let's say here, I'm looking now at one direction only, but also the same direction is nothing. And we have a simply supported, this is not the simply supported beam now anymore, because it's got multiple brackets. And that's basically what we see, okay? We have multiple brackets, very long beam with multiple brackets. Okay, so if we calculate deflections of this, and you can do that, that's not difficult. You can do it by a simple calculator. You don't need to have a big computer power. That's a classical method. That's the equation, how you do it. Basically, that's the deflection. So deflection y, that's z-axis here. And when we apply load here, we can calculate from this formula everything, really straightforward. Obviously, we need to calculate, we need to know the reaction forces here. So when we know F, we calculate those. The problem is that this is in classical mechanics, it is referred to as not a so straightforward model. It has got some difficulties because we need to have additional equations to solve it. But anyway, you can solve it. And if you solve it, you can come quite quickly to some results. All right. This example here is limited to 3 spans. So 3 spans means if you have here 1, 2, n minus 1 n, you have plus 0, you have n plus 1 brackets, and we now do the calculations of maximum deflection of this model. That's the result here. So the result is, okay, when we apply the load here in the middle of the first span, the maximum deflection is 7/48 times FL cubed EIX. Everyone knows what is F, what is load, what is L. L is the spacing of the brackets, E is the Young's modulus, and I is second moment of area, so XY. And that's the undergraduate mechanics or even less. So now when we slightly change this coefficient, you get 0.7, 7/10, 48. And here it is. That's 0.7, that's the coefficient alpha. So the code in 81 is using 3-span beam model. That's the answer to the question. And obviously, that's a common knowledge in some probably advanced analysis, which people know mechanics, but from my experience, not everyone knew it. So that's basically the conclusion 1. We use 3-span model. Now, okay, when you do deflections and you go to bending, and bending is key issue, what next? Okay, is it enough? No, we need to look at stress. Stress. Okay, so what we would do? We could take this beam and now find with the maximum bending moment, because there's bending here. Well, you go to EN 8150, and there is this equation for maximum bending moment. And this does not relate to this model at all. It's not. It is based on the model here is on the right-hand side, which is not a simply supported beam. It's not multi-span. It's a single span beam with one end simply supported, with simple support, the other one, which is called fixed or built-in, okay? And then the maximum moment is given by this formula, which is in the code. So clearly now, the code asking us, And we don't see it in the codes. In the code, you always have this, and obviously you have this equation. When you have a moment, you calculate the stress maximum moment by the section modules. Everyone knows it. Okay, so that's basically. But this is not based on deflection model. There's another model, and again, we know this is worst case condition. So we use worst case condition for deflections, and the straightforward model is 3-span simply supported beam, or beam supported beam, and here we use another model. Okay, if you calculate it here, maximum deflection for this, and if we use this model, it wouldn't work because the maximum deflection for this beam when we apply here the force in the middle is at the sort of more or less at this point with 0.5 L, that's about it. And the maximum deflection is 0.093. And we saw earlier on the 0.7 divided by 48, that's different and that's less. So much smaller value than for the case of 3-span beam. Okay. Now we know, okay, so that's quite clear, and we use this formula, and then we get maximum stress, and then with deflections are within the limits, and stresses are within the limits, we are okay. Okay, so now, all right, what about with this? Well, really quite simple equation, isn't it? This is not much involved. You can do it by hand. We teach it in our lift courses, we teach it in mechanics. Everyone who knows mechanics would do that, okay? So now let's have a look at another point which is linked to it, and I wanted to a little bit discuss about bracket spacing and what will be the design calculation now, because clearly everything depends on the spacing of the brackets. Okay, so that's again, here we've got the two equations for deflections. Again, I stick to deflections. And we know now where they're coming. It is from this 3-span beam model. And the clause here is, in EN 8120, 572.12, the combination of deflections of guide rails and deflections of brackets playing the guide shoes and straightness of the guide rails shall be taken into account in order to ensure a safe operation of the lift. All right, so that's why, okay, we have to look at this. That is taking some additional component, but the first and don't, okay? So if you apply, obviously, only this model, it doesn't take into account play in the brackets, anything like that, okay? It doesn't take into account the structure of the building. So what about the structure of the building? We know that at some stage was quite a lot of discussions on IMA-HE4. So, okay, so you have now we've got looking in N8120, and if you look in Annex 2, sorry, E2, there's a descent, that's highlighted here. It is important that the guide rails of the lift are supported in such a way that the effects of movement of the building structure to which they are connected is minimized. Okay, so we are looking to minimize. Very often that assumption would hold, okay? But sometimes not. And we know the discussion for tall buildings that might be different. Okay, so when considering buildings constructed of concrete, okay, blockwork or bricks, it can be assumed that the guide rail brackets will support the guide will not subject to displacement caused by movement of the wheels. All right, that's reasonable. This is reasonable. However, and again, there's another paragraph here which says you cannot use assumption when there is steel structure or wooden structure. That you need to take into account. So then, all right, we need to then look and take into account those. And analytically, that we are in trouble. This would not, the guide doesn't prescribe us. So obviously, most of this kind of work can be done using FEM, and we know that CAD systems. All right, so where we go from here? Right. We don't do it, we don't use it. Yeah, we do, we should use, and I always advocate that this is a simple formula which gives first evaluation. So when we teach our students, we want them to use those formula in the first case. And okay, later on, if someone goes to CAD, models everything, at least this gives the first approximation. And you would see then that it's a complex model done in SolidWorks or ANSYS or anything else would make sense. And that's the way which we want to approach this problem. Okay, so simple example to demonstrate again with deflections how this could be done quickly and efficiently. Again, the basis here would be EN81 and the permissive deflections 5 millimeters for the car. All right, let's have a look here. So that's an example. I'll go. We have two graphs here. Okay, it's not that complicated. Just don't worry. I'll explain. That's one graph. The second graph. And we take here in this example conventional car frame, a car rated at about 1,200 kilogram. And now the subject is to safety gear application. That means, okay, what it means that we need to use acceleration, deceleration of additional 1g. Okay, so basically that's the case, additional load. Now, when we do the calculation for this system, we know that we can calculate the forces in both directions, Fx and Fy. They are bending forces now, which would accommodate deceleration or acceleration, if this acceleration could be, or braking, but this is progressive safety gear, so this operational gear. And then we could calculate, we can draw two simple diagrams based on those equations, but without the structure, okay? So we just take them away. So without the structure, we can calculate two characteristics. From this equation, the characteristic would be the y value of the second moment of area in terms of L, and it will be cubic polynomial, and the same for Ex. And then we assume that we are imposing deflection 5 millimeter here, that's permissible, and we come to those blue line, all right? And that's about it, because now we can go, say, to ISO standard. We can choose, say, T89B or T125. Then we draw horizontal lines where we have those values Ex, and then intersection, you can see what is coming from here. We need to take actually the second characteristic here to come up with the spacing which is statically safe for the system, which is here is 2.95, what was it? Okay, here, 2.95 for based OIX. That's the maximum spacing which could be for this rail, or you can take bigger one, then you'll get larger space. Okay, so spacing, right. This would give us this to meet the condition 5 millimeter for the car. Okay, now we would need to still check the stress, and then we'll be using the other formula. Okay, but that's obvious, so I would not go any further. So this would demonstrate 5 millimeter would meet the condition for the standard. Okay, is it good enough? Is it good enough? All right, no, it is not be good enough, because we know that, for example, some manufacturers, and there is Savira, which everyone is looking for, and they say, no, this will not do good ride quality. So, okay, now I want to explain, again, using some numbers, why not, okay? Why not? All right, so let's go here. So to maintain ride quality of a lift, required guide rail deflection limits should be much smaller, right? And Savira is saying something like 1 millimeter maximum for slow lifts. I think this is 4 meters per second. And anything above 4 meters per second should be half a millimeter or less, probably. Okay, and where is this coming from? Why is it up? Okay, again, that can be easy seen when we look some models. Okay, there's now looking into different models. They are not static models, they are dynamic models. So we are looking at the dynamic conditions. So we have a system which, say, satisfies static conditions, deflections and stresses are okay, but now you're looking at dynamic conditions and the right quality. And then you are saying, okay, 1 millimeter is not enough. Half a millimeter is not enough when there's a higher speed. Why higher speed? Okay. Now take a simple example. When we take a car with a frame, model is a simple mass. So again, we're talking straightforward models, okay? That's nothing very excessive. And here you've got guide rails on both sides. And the suspension, there are guides, okay? Roller guides or sliding guide. That's a model as through spring and damping elements, all right? So now what we do, let's take the worst case scenario. These guides, okay, is a red line here. That's imperfection, a badly bent, okay? The bend and they form this kind of wave. All right, can happen, it can happen. And then obviously we've got spacing here. That's our multi-span beam, okay? Not simply supported. So, all right, if we now take this wave and the car is moving at speed, on this wave, what happens? Okay, we look now at this simplified model. We simplify this further, and basically when the car moving up and down, we replace those springs with equivalent springs, those dampers with equivalent dampers, and basically this mass is subject to what the load is called base excitation. And again, that's nothing new, that's undergraduate dynamics. And basically then what we have, we drive the car along this wave. The frequency of this wave can be calculated readily in terms of guide bracket spacing through this formula here. There is V, this is speed, divided by what is here, the length of the wave. So what is the length of the wave here? From here to here is 2L, okay? So obviously guide bracket spacing will affect it. And the higher we go, the higher frequency is. V, let's say 5 meters per second, and then we take this to L, divide it, and you've got the frequency. And that's what is linked to the Savira or any other manufacturer's recommendations, because that's the issue, is the frequency. Speed is related to the frequency. Okay, so for this, I need to go back here, and some analytical, simple equations, nothing computerized at that stage. Basically, what you have, when we apply here this wave can be treated as simple sinusoid, harmonic, okay? With the frequency omega, which is calculated here, depends on the speed, depends on bracket spacing. So we apply this motion here, and what happens then? This mass is moving. So the motion at the base is S, the motion of the car mass is x, and now what is x by s? X maximum by s maximum can be given via this simple formula, because x is also sinusoidal, it comes from simple mechanics, and with the frequency of the guide excitation. Okay, so then we arrive to this expression, which is in terms of basically 3 main parameters, or two. It's the ratio of 2 frequencies, omega of the guide, and the natural frequency of this mass. We know that structure has got natural frequency. Now, that's a ratio R, omega by omega n, and then we've got some damping. Obviously, damping is coming through here. So what we have, you can plot now this against the ratio of the frequencies. And what we find here, depending on damping, we have large transmissibility. That means when we put input 1 millimeter, to this case, when R is about here, is 1, that's the region for small damping. And you see here, 7, okay, quite close 7. For you put 1 millimeter, you get 7 millimeter. You take half millimeter, you get 3.5, or roughly. All right, this is illustrated through the simple experiment in the lab. This is base, okay, nothing to do with the rail, but that's a base, moving base. That's the structure here. And this structure has got about natural frequency of 5 Hertz. Now when we come to this place, right now, we've got resonance. So that's basically what we are getting from a badly bent guide rail. It's a resonance. So again, everything is going down. So that's a simple model, straightforward model, okay? But now no static, it's dynamic. Then I come back. All right, when we want to now get a bit more involved, I'll just go very quickly through this example. I think I have still a minute or two. Then we can use more involved model, okay? This model has got 2 masses which can move horizontally and we can rotate. Okay, then there's a bit of number crunching involved. We need to use this equation which needs to be solved, and that has got 1, 2, 3, 4 coordinates. And this system, we have not just 1 frequency, but 4 frequencies. So when we look here, put some numbers, that's the simulations for 10 meters per second, the guide spacing 2.5 meter, and again, it's going over when that is badly bent. The result is here. That's the frame, horizontal motion. That's the car, horizontal motion. Take this. It's here about, you see the deflections, 0.5, about 7 millimeter. 7 millimeter, that's the frequency spectrum. At 2 Hertz, it's a not good outcome, because that gives us acceleration of over 100 milli-G peak. All right, so here we go. We have 1 millimeter deflections, and is dynamically would not be satisfied. So that's about it. So let's do some quick conclusions. The safety codes and engineering practice have established some straightforward models and criteria for a lift guiding system to be designed with adequate strength. True. These models can then be used as a starting point for evaluations of lift ride quality. Okay, yeah, okay, sort of, because then we need to still consider the support conditions, how they are supported, and then again you need to go back to static, whether we have 3-span beam or we've got supported and fixed beam. But with static calculations results meeting the code requirements, okay, the dynamic conditions need to be carefully considered. So that's the end of my presentations, and thank you very much. And questions, please.
Yeah, hi, Graham Barker from Cundall. So the calculations assume that the guide rail is a single beam. So what's the impact of the joints of the guide rails?
It's another story. Joints are considered, is linked to the joints, and that would be pretty much linked to the spacing of the brackets. At the joints you would have, let's say you guide along 5 meters, okay? So that means we have a bump every 5 meters. And actually the result will be pretty similar to that, because here in this example it was wave, but here you would have a bump, 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 bump. When you calculate FFT on these bumps, you would pretty much come to a sinusoidal function with a frequency of the same as here. So these models can be applied for many scenarios.
Professor, thank you very much. I mean, it went way above my head.
Okay.
So what I'm going to be talking about is a practical situation which is out there. So I've been trying to drill down with companies that I work with as a consultant.
Yep.
2 things. One is the calculation on rails, and the other is the traction calculations. And in this commodity product era, the expectation or the thought process is, about 10, 15 years back, somebody might or might not have done these calculations. Okay. So it's like this: if X rail has worked all these years, we continue with it. But the problem is, this X rail is no longer X rail. The weights have reduced, the thicknesses have reduced, and if any of you have been following Lexian from China, he's the president of the Chinese Lift Association. He's been talking about it very critically, that in the process of this, disposable lifts, this has all been reducing.
Okay.
Where do you think it's going to be ending? Where do you think we are headed?
Well, I think those calculations are still valid for anything.
No, it's valid, but provided somebody does it.
Provide, sorry, for what?
Provided somebody actually
Of
backs
course,
up.
yes. That needs to someone done. But you've got this. If you go to severe recommendations, this what they say? Okay, 1 millimeter, half a millimeter. That's exactly what it is. They're coming. As soon as we understand where those come from, we are safe. So the point is about training and education. We need to train our technicians who are involved in this. They understand principles of mechanics and principle of electromechanics, principle of electrical engineering. Overall, principles of engineering. That's the main point, and that's what we need to deliver. So we, as a educational trust, we are organizing those conferences exactly for this purpose. So that means we need to train, and we have on our course, we have assignments which actually students do that, and we try to them understand that as much as we can.
I think that concludes.
Okay.
Thank you very much.